thrill for me to come down to Lethbridge, because what you may not know is that it is widely known that Lethbridge puts on the very best Brain Awareness Week in the province and probably nationally. And if you have one of the very best Brain Awareness Weeks nationally, then you're competing internationally. So good on Lethbridge and the University of Lethbridge and the community for coming out and taking part in Brain Awareness Week. So it's a thrill for me to be here. All right, how your brain maps the world. This is not a map, this is a photograph, and of course most of you are going to recognize that this is a photograph of Calgary. It's a very nice photograph of Calgary. I bought this photograph 20 years ago to show in my presentations, because when I go to other universities, I'm always trying to recruit graduate students or postdocs to my laboratory. And so I'm showing off Calgary with this photograph. And I have used this photograph dozens and dozens and dozens of times and never really looked at it. And I was just in Japan in late January, and I gave a talk in Okinawa at the Okinawa Institute of Technology. And while I'm just introducing the topic, I've got a hand up. Someone wants to ask me a question. So sure. What's your question? And they said, well, do you have dinosaurs in Calgary? And I said, excuse me? Yeah, there in the picture, there's a dinosaur. Now, Brian, if you'll advance one click. It's a brontosaurus. That's at the Calgary Zoo, for those of you, it's a brontosaurus. I have never seen the brontosaurus before in this picture. I've used it dozens of times. So I said, yes, we have dinosaurs in Calgary. They're tame though, dinosaurs. But we like to keep them on the island so that they don't interact with the traffic downtown there. The Japanese are so polite, they accepted it. So that's not a map, that's a photograph. Brian, if we could advance, please. Here's two examples of maps, right? So on your left, we've got a map of Canada with Lethbridge, Alberta in it. And that's a low-resolution map. You know where Lethbridge is. It is not in the middle of Hudson's or James Bay. It is on the southern border. It's not in the far west. It's not in central Canada or eastern Canada. So that's just a general idea of where Lethbridge is. That's contrasted with the map on the right, of course, which is a high-resolution map of Lethbridge. And it has some essential features, the Oldman River, Henderson Lake Park. These are, you're probably looking to see where your house is or something right now. It's not that high of a resolution map. And there are things missing in that map, like you don't have an appreciation for the depth of the coulee, the very impressive coulee in that map, right? And you don't have an appreciation for the train trestle, which of course is a landmark for those of us who aren't from Lethbridge, probably is for people there in Lethbridge. That's not in this map. But it is a representation, and a very accurate representation, if Google has it right, of Lethbridge. And I'm going to use those two maps as sort of metaphors for brain maps, all right? Right. So then this is a human brain. I'm going to assume that you've seen one before, but we'll just talk about some of the main features. So this would be a view from the side, and you're looking at the left side of the brain, okay? So the front on the far side, the back here. Tucked underneath it is the cerebellum, that brownish area. And what I mean by a low-resolution maps is that we have these different areas of our brain that are used for different functions. So at the front end, we have what's known as the executive area of the brain. This is the area of the brain that's responsible for decision-making and planning and these sorts of things. So if you're in a car accident, and your skull stops suddenly because it's hit a windshield because you didn't put your seatbelt on, what happens is the brain is sitting in fluid inside your skull, and it has a momentum, and it charges into your skull, which has already been stopped by the windshield. So now your brain, front of your brain, has an injury because it's going to impact the skull. And what sort of deficits would we expect from someone who has this sort of injury? Well, you would expect executive function problems, problems with planning, problems with decision-making, those sorts of things, okay? And sometimes when we have accidents like this, we hit so hard and the brain smashes into the front of the skull so hard, it then rebounds and hits the back of the skull, okay? It's called a coup and a counter coup. And then what happens is you have problems with vision, because vision is located in the very back of your brain, back here. Okay. I'm going to point out the auditory area next. So that's the area that processes sound. And we're on the left side, and I'm going to come back to left-right differences later in the talk. And then just above it, there's a label, is aphasia. It's not a very, very good label for this brain, but what it really should mean is it's the area of your brain that's responsible for understanding language. It's also known as Wernicke's area, named after Wernicke, who discovered it. Okay, and it is beside the auditory cortex, and that probably isn't an accident. And again, we'll come back to this. In front of the auditory area, we have the speech area, also known as Broca's area, and that's because that's the area of the brain that's responsible for generating speech movements. Movements of the lips, movements of course, your vocal cords, because that is all motor behavior. When we think about motor behavior, we think about walking around and using our skeletal muscles. But of course, moving your vocal cords is also a behavior, and it requires neural tissue to do that. And it's not a surprise that the speech areas are right beside what we call the motor strip. And that thing is responsible for making voluntary movements. It's responsible for making strong muscle controls from everything from your fingers down to your toes. And right beside that, the somatosensory area is the same representation of your brain, on your brain, but that's of the sensory information coming in from your skin all over your body. So that's right beside the muscles on the brain. Okay? So this is a low-resolution depiction of your brain. And by the way, this is a very beautiful brain. It's been cleaned up. There aren't any blood vessels or membranes or anything yucky there. It looks really nice, doesn't it? And I was showing this to my wife the other day, and she says, now she works in the cardiac field, in the nuclear medicine field. She's not a neuroscientist, and she says, it just looks like intestines to me. And I said to her, well, do you think that's where the phrase shit for brains comes from? And she says to me, promise me you will not say that in Lethbridge. I said, okay, honey. So how did we learn about those different areas of the brain, those areas of specialization? And a couple hundred years ago, we learned it mainly from wars, and then more recently from car accidents. So what happens in wars is we shoot hot pieces of metal at each other, and very often it'll cause a penetrating brain injury, but the person will live and show some sort of deficit for the rest of their life if they survive it. And then at autopsy at the end, you can look at part of the brain that was damaged and match that up with the behavioral deficits that the person had and go, oh, yeah, that was the executive area. Joe wasn't very good at making decisions after a bullet went through his frontal cortex, okay? Or the visual area, or whatever it was. Today, we still get information from gun shootings in the United States, but in Canada, it's mainly car accidents that we're getting those, or strokes, where we get those sorts of information. But in the last 50 or so years, we've invented new technologies, and we're getting better and better resolution and more accurate determinations of what areas are doing without lesions, without penetrating head injuries. So this fellow, Wilder Penfield, great Canadian, there's a boulevard named after him in Montreal, and he worked at the Montreal Neurological Institute as a neurosurgeon. What he did is he created craniotomies, which is to say he took away part of the skull, exposed the cortex, and then used electrical stimulation on the surface of the skull, the surface of the brain, to determine what areas were doing what. Now these patients are conscious and awake, not anesthetized. They have local anesthesia at the wound here, but they are fully awake and can respond to commands. So if he touches the somatosensory area, let's say for the fingers on the left hand, the person can go, oh, I feel something in my left hand. Well, there's nothing touching their left hand. He's touching that area of the brain that controls the fingers of the left hand. If he moves just a little bit more forward and stimulates, he'll actually cause the fingers to move, right? If he goes to speech areas, he can interfere with speech. If he goes to auditory areas, patients will say, oh, I just heard a little bit of music. Well, there is no music in the operating theater up there. He's just stimulating that part of the brain. And he actually did use little squares of paper with numbers on them and placed them on the area of the brain that he just stimulated, and he took careful notes of what areas of the brain were responsible for the particular behaviors that the patients could talk about. And that is one of the most modern techniques, that was 60 years ago, 60, 70 years ago, for discovering different areas of the brain and what they did. And so Penfield made a map of the brain, both the auditory areas and the visual areas, and of course the motor and sensory areas. He was also very interested in consciousness, and our friend Ian Wishaw has written nice stories about that. Okay, Brian? So this is Penfield's homunculus. Homunculus meaning little man. It's very sexist. It could be little woman, of course, if it was a female patient. And this, I just can't get over this particular depiction. I can spend hours looking at this. And what we see here on the far side is that's where your toes are represented, down that far side. And next to the toes is the ankles, and then the knee, and then the hip, and then the trunk, and then the shoulder, and then the elbow, and the wrist, and the hand. And they're all lined up, and we call this topography. They're lined up topographically. Okay? And pretty much everybody's brain is organized this way. Even though Penfield was working in patients that had either tumors or epilepsy, he just didn't take people off the street in Montreal and take out their skull and stimulate their brain. These people were potential candidates for surgery for either tumor removal or to remove their epileptic foci. I love that picture. There's an error in the picture. There's a big one in the picture. Now you can't see this, but at the very bottom right-hand corner is the initials HPC, which stands for Mrs. H.P. Cantilli, who was the graphic artist that drew that rendering. And when I look at the photograph or the map, my eye immediately goes to the body representation, and I don't really look at the words unless I'm forced to. And I think everybody does that. You go right to the body. Okay, here's the error. Well, before I get to the error, I'm going to just wait a second. We'll get to the error. I want to talk about John Hewlings Jackson first. We knew before Penfield made this map that adjacent muscle groups were organized beside each other. And we knew it 100 years before Penfield. And it was John Hewlings Jackson that described this. John Hewlings Jackson's wife had epilepsy, and her seizures manifested in a particular way. They would start in one area of her body, like her fingers, and her fingers would start to have contractions. And then the wrist would become involved, and then the elbow would become involved, and then the shoulder would become involved, and then the leg would become involved. And it was Jackson, again, 150 years ago, that figured out why. The reason is that the brain is organized with adjacent muscle groups right beside each other or adjacent to each other. And the seizures spread from an initial start, let's just say the fingers, and then propagated back and brought in the rest of that musculature into play. And we call that today a Jacksonian march, when seizures manifest that way. But it took 100 years before Penfield came along and essentially verified what Jackson had said in his writings. Okay, now we'll get to the error. See how the face is right side up? It's not. It should be upside down. It should be the other way. So the toes and the ankle, the legs and the hands, that's all correct. But the face, you have to twirl it upside down. In other words, the chin representation, the bottom of the face, should be next to the fingers on the representation. So how do we know this? Because I went to graduate school with a guy named Phil Servos, that's why his name's on the screen, and he used a technique called fMRI, functional magnetic resonance imaging. It essentially just tracks blood flow where it goes in the brain, and found that when you stimulated the chin, you got blood flow changes close to the fingers, and when you stimulated the forehead with air puffs or something like that, you got blood flow to areas away from the fingers, closer down to the tongue and vocal cords. I learned about this in 1999, and I just thought, wow, that's cool. And then I've spent the last 17 years or so actually looking at the relationship between those kind of maps and people with epilepsy in my lab. All right. Primates. It's not that Penfield mapped humans out of nowhere. People had been mapping other primates, like monkeys, including chimpanzees, they're not monkeys, including apes like chimpanzees, and all of those primates have an upside-down facial representation. So it was kind of weird when Penfield and Mrs. H.P. Cantilli came out and said, oh no, the human face is right side up, because it would be weird that all the primates have upside-down faces, but humans have an upside-right face. It just didn't make sense. And of course, Phil Servos then showed, in fact, the human representation of the face is upside down like the rest of the primates. Now, we also knew this before Servos did his experiments, because some people in industrial accidents or for whatever reason will often lose a hand. This happens, right? So if the hand is removed and the stump heals, if you then press on the stump where the nerves that feed the hand that's now missing are still present, so the nerves that feed the hand are still present, but they're there at the stump. If you stimulate the nerves of the hand's missing there, you get sensations in the bottom of your face, not the top of your face. Well, why is that? Because actually the representation of your hand and the representation of your upside-down face overlap. Okay? And especially in the case where you lose a hand, the other areas will expand the representations and overtake that hand area. And of course, it's the chin, who's next to the hand, that overtakes it, not the forehead. And when I learned this story again so many years ago, I just fell in love with it. Now, Penfield never really properly acknowledged the error. And if you talk to people at McGill, they want to blame Mrs. H.P. Cantilli, but I got to tell you, it's Penfield's responsibility, not the graphic artist. What Penfield did say about the map is that, because this is iconic, this is in all the textbooks, this is famous, is he always understood that it was a representation that had a problem with it. And the problem wasn't that the face was wrong. The problem is it's the smooth representation from the toes to the hand, as if it's a smooth body laid out in your cortex, and it's not. It's islands of movement. The ankle would be an island, right? The knee would be an island, and these islands overlap. So think of this more like a Picasso painting. It's the way your brain is really organized, eye up here and face and everything, like a Picasso, as opposed to the beautiful diagram that Mrs. H.P. Cantilli drew. Okay, Brian. Yeah. So then this is a 3D figurine that was created. It lives over at the Natural History Museum in London. It's called a Bridgman image. And so what this artist has done is, using clay and in 3 dimensions, represented the amount of cortex devoted to different areas of your body. So what this tells me when I look at it, I love this figurine, is that we devote one heck of a lot of cortex to hands. And we also devote a lot to lips and, of course, vocal cords and tongue, because it's all about verbal communication in our species. And so we need an awful lot of gray matter, an awful lot of brain matter to run your hands, fine, dexterous hands, and to run your mouth, okay? And when I think about our species, yeah, we're really good at using our hands, we're doing it all the time, and we're putting things in our mouth all the time. This is the world's very best grandbaby ever. Happens to be related to me. It's funny how that works out. And this is her world in the bath. Everything is grabbed by the hands, and it instantly goes into the mouth. And I think it's not just, I think she's 6 months old in that picture. I think we do a lot of that as adults too. Hands and mouth, hands and mouth. So it's not just people that have motor maps. Other mammals have motor maps. And in my laboratory, we discover and we probe the motor map of rats. So instead of a homunculus for our species, Homo sapiens, this is a ratunculus. And all it's meant to show, this map here on the right, is that the body of the rat, the musculature of the rat in this case, is laid out across the cortex. So again, the anterior or nose of the map would be up here. So here we have the jaw, and here we have the neck, and then a big whisker area. There's a little digit there. We have lots of wrist, okay? Some elbow, and then we get back here, we have trunk, and not a lot of musculature in the trunk, and then we have hind limb and tail. So we go from rostral to caudal or anterior to posterior, and we have a ratunculus. I'm going to show you one quick study on rat motor mapping in a second, but I'm just going to take a pause here and say, has anybody ever wondered why scientists like to use fancy words like rostral and caudal when everybody else would say nose or tail or up or down? And when I showed that picture of the brain, those are gyri and sulci. Why don't we just call them hills and valleys? Have you ever wondered why scientists talk in a language that only other scientists can understand? Does it drive you crazy? There's a reason for it. And the reason is actually a simple one. We don't want anybody to understand what we're talking about. No, that's not true. The reason is that in living languages, the meanings of the words changes as the language evolves and changes. And so if we're going to label structures in the brain, for instance, we want to use monikers, we want to use words that aren't going to change. So we steal from dead languages like Latin and ancient Greek, and we name those things in Latin or in Greek because those languages are no longer spoken, and therefore the meanings of the words won't change. And that's why scientists talk funny. And when we bring students in our lab, we train them to talk funny, and what we're really doing is we're training them, hopefully, to be precise and concise and use very well-defined words. And the problem with that is when students or faculty sometimes want to talk to real people who pay their taxes that drive our research, sometimes we forget to talk in normal words or normal language. So if I've said anything that's bizarre, stop me at the end and we'll go back and give you the right word for that. Okay, Brian, next map. These are 4 motor maps from 4 different rats, and I decided to show you that drugs can change the expression of a motor map. And I decided for the purposes of this talk to talk about THC. THC is tetrahydrocannabinol. It is the active ingredient in cannabis, otherwise known as marijuana, which became legal in this country on October 17th of last year. And THC binds with a receptor called the CB1 receptor, and it has effects on the brain. Now, I could have chosen any number of drugs. I could have chosen alcohol, which has been legal forever and mostly, in most places, and has probably been used by our species for somewhere between 7,000 and 10,000 years. We've had alcohol, but I didn't. I didn't choose to talk about methamphetamine, but I could have. We're in the middle of an opiate crisis. I could have chosen fentanyl or Oxycontin, but I didn't. I just decided to use this one drug. And the different drugs have different effects, but in general, they either are excitatory or inhibitory, okay? They either raise activity or they dampen activity down. THC changes the activity depending on the dose. So there's a map on the top left. That animal is the map of its forelimb, its wrist and elbow and shoulder, just the forelimb area. In the map on the right, a rat has received a tiny little bit of THC, maybe 1 toke's worth of THC, very little, okay? And the map, it might be hard to tell, but it actually got bigger. Excitation 1, it's a little bit larger. But then when we go to the next dose of the drug, which is the bottom left, it's a medium dose, the map got noticeably smaller. Statistically significantly smaller. And if we go to a high dose of THC, like a Woody Harrelson dose, or I don't know, a Bob Marley dose of THC, then the map got really small, and some animals it actually went away. We couldn't derive any points because inhibition one with THC. So what I'm telling you is while alcohol is legal and cannabis is legal, that doesn't mean it doesn't have real effects on the brain and can change the brain either on a short-term basis or a long-term basis. All right? All drugs can do that if given in a high enough dose. Okay, Brian. Okay, so I'm going to talk about dystonia for a moment, and I've chosen this photograph. It's a young woman playing the violin. Violinists happen to be very susceptible as a group of people for dystonia. So what is dystonia? Dystonia is a painless loss of muscular control in highly practiced movements. So if you want to be really good at playing the violin, I mean orchestra level violinist, then you're going to be practicing 6 hours a day, every day from, a very young age. And the same movements will be practiced over and over and over again. I'm not talking about the hand so much that's controlling the bow. I'm talking about the fingers that are on the strings. Okay? Practice movements, highly practiced movements that have to be precise and exacting. And a proportion of these people, at some point in their career, will actually lose muscular control and not be able to make the precise movements that they were able to make a week ago or a year ago or 10 years ago. And that's dystonia. Okay? So the reason I'm telling you this is that when you do an image of a brain of a person with dystonia, you can actually see that their maps are different. Their maps have a functional problem with them. So here we have two images, and these are called coronal images, okay? So imagine me, I'm looking at you, my chin is up, and we're going to take a big saw and we're going to cut right down here, and the front of my face and the front of my brain's going to fall off, and you're just going to look at a section. That is a coronal section, and that's what this image is showing you, okay? These are the ventricles of your brain. They're fluid-filled, so you do have holes in the middle of your brain. You've always suspected your partner had holes in their brain. We have the evidence right here. Okay, so this hand is not influenced by the dystonia. And you can see that each digit 5, 4, 3, 2, 1, have separate representations. They don't overlap. Just like your fingers are separate, the representations in your brain are separate. But what happens in the affected digits of people with dystonia is that the representations overlap and they lose that muscular control. The very precise and highly skilled muscular control goes away. So that's in this case and in the far side, two different individuals, one right-handed and one left-handed. Okay, so that sounds serious. If you're making a living playing the violin and now you can't play the violin and you've just spent 20 years, 6 hours a day, playing the violin and now you can't move your fingers right, that's what we call a problem, right? A problem is anything that can't be solved with money, right? That's a problem. So what's the solution? It's a very simple little study. What they did is they took people with dystonia, violin players, and they had this little device with these little tabs, almost like piano keys that stick out, and you put your fingers on these keys, and you just move them up and down in a certain sequence. And you stop playing the violin for a while. And you can see that the muscular movements of the third finger don't look like the muscular movements of the third finger on the opposite hand. This person has dystonia. But they practice on these keys, and they don't play the violin, and a couple of weeks later, it looks right. It looks right. And guess what? When you do the imaging to find out the representation of the fingers on the cortex, it's gone back to typical. They no longer overlap. So a very simple behavioral treatment can change the motor map and restore the person's ability to play fine, highly practiced muscle movements of their fingers and play the violin again. No drugs, no electrical stimulation. That's what I call a success. Okay, so I'm going to leave the motor cortex now, and I'm going to go to the auditory cortex. So that's the area of your brain on both the left side and the right side in which you detect various pitches or tones, sounds. So you have low frequencies, like 500 hertz, which is anterior. And then right beside it, you've got a different area that's responsible for detecting sounds or pitches at 1,000 hertz, all the way up to 16,000, the main range of human hearing. And that is called tonotopic organization. And it works on the left side of your brain, and it works on your right side of the brain. And it's pretty much the same for everybody who's a hearing individual. And then every once in a while, someone will go in and they'll get their hearing, not only their hearing tested, but they'll get imaging of their cortex. We always expect to have low frequency to high frequency in this orientation. And then every once in a while, someone will come in and it'll be exactly the opposite. It'll be high frequencies on one end and low frequencies on the other. And these people hear properly, and these people hear normally. It just so happens that their cortex is organized backwards to everybody else. Now, I told you earlier that my wife works in a cardiac clinic. Every once in a while, so she does heart imaging all day long in people that have been sent to the clinic because there might be a heart issue. And she will come home about once every 6-7 years or so and say to me, "Yep, we did a guy today whose heart is backwards." So you know these things exist. Your heart has a particular orientation. Left chamber, the big one, the left ventricle, right, the left and the right atrium. One side, like the left, sends it to the body. The other one sends it to the lungs to get oxygenated, then back to the heart, to then send it to the body. And every once in a while, some guy will come in off the street and his heart is backwards. I mean, it's backwards. And he's alive. And this is just thought to be astounding. It's the same thing with the auditory cortex. Every once in a while, someone comes in, they're functioning, they're alive, they're in their 50s, and it's backwards. So it reminds us of something. It reminds us that we did not inherit an auditory cortex from our parents. We did not inherit a heart from our parents. What we inherited from our parents was a program to make a heart. We inherited a program to make an auditory cortex that is tonotopically organized this way. And just every once in a while, the program is executed a little bit differently than everybody else, and you can have a backwards heart, or you can have an auditory cortex that is backwards as well, and still it works. Okay. Now, handedness comes into play. It actually depends on how you process music and how you process language if you're right-handed or left-handed. So we used to believe that left-handers were evil. Okay, and we've gotten over that. But I'm here to tell you that my wife is left-handed, and never mind, I better not say anything. I see that I'm being videotaped, and if she finds this videotape and I call her evil, there's going to be heck to pay at home. Okay, so in our species, about 15% of people are left-handed, and that's fairly stable in cultures that don't punish people for losing their left hand. And there are still cultures today that punish people for using their left hand. My wife's grandmother didn't want her to lose her left hand. My wife's grandmother had 2 female grandchildren. Both were left-handed. It just drove her crazy. But my wife resisted because she's built that way and used her left hand. But it's about 15% at the population level. If you're right-handed, then you will process, in almost all cases, language with your left hemisphere, and you will process music with your right hemisphere if you're right-handed. Okay? If you're left-handed, about 70% of left-handers process language and music just like right-handers. But then the remaining 30% of left-handers actually split into 2 groups, where they are the opposite, where they will process language with their right hemisphere and music with their left hemisphere. That's about 15%. And then the other 15% will use both hemispheres relatively equally for both language and music. So here's another example of maps, in this case auditory maps and language maps, that actually depend on hemispheric specialization and whether you're right-handed or left-handed. And that means to a certain degree that they are plastic and that they can change with experience. Okay, so we have talked about where understanding language is and Wernicke's area, and so I just want to show you this particular image. Again, it's a person facing in this direction, it's the left hemisphere, and this is where Wernicke's area is, okay? So, the question at the top is, what map is active in the deaf who learn sign language? So for most of us, we think of language as spoken language, and we detect spoken language with our ears and our auditory system, and we interpret words and sentences and the meaning of things. But for those individuals who are born deaf, who cannot hear, and there's a wide range of reasons why that might be so, they can learn sign language, okay? ASL, American Sign Language, is what we learn over here. But across cultures, there's all sorts of different sign language. There's BSL, which is British Sign Language, that has slightly different rules, well, actually in some cases large differences in rules for American Sign Language. So sign languages across the planet, but they're not all the same. Where they are all the same is, of course, they're sending visual information to you by using hand signals to convey meaning, all right? So is that language? If I say, you know, ASL, you figured that out, so that's got meaning. That is a language, right? If I say this, anybody want to tell me what this is? Milk. Yeah. Right? Okay. So that tells me that language isn't really related to auditory areas necessarily, right? It's also visual. But when we put a person in a magnet and we record their blood flow while they're perceiving American Sign Language, actually in this study it was British Sign Language, what areas of their brain have enhanced blood flow? Language areas. So even though the information's coming in through the visual system, for most of us it comes in through the auditory system for language. In these individuals with experience with British Sign Language, BSL, it's their language areas that light up just like you'd expect, even though it's a visual input. And that's how interconnected your maps are. I showed you that map at the beginning where it's, you know, vision separate from audition. I'm now telling you a slightly different story, that's in neurologically intact individuals, but in individuals that are deaf, they're using auditory or language areas to do language, but it's visual language. Okay, let me give you another example. We're going to move to the visual system. We probably know more about the visual system than any other particular sensory system. I think the reason for that is that we're a highly visual creature. Seeing the world is so important to us. We collect so much information. And so as researchers, we've spent a lot of time working in the visual system of humans and other species. So the first thing you need to know, your eyes collect visual information. They project to the back of the brain, as we discussed, and look at that. The blue is represented for the right side of the visual field, and it is taken in by both eyes, but in our species, they cross and stay on the same side, and so there, the blue is represented, the right visual field is in the left side of the brain, and vice versa. The left visual field is in the right side of the brain. So the brain is highly organized, and we're going to have a visual map. It's just that it switches sides. Okay, now we have a fovea in our eye that's responsible for color vision, and it has very dense photoreceptors, and that's why when you're paying attention to something, you usually put your fovea on it. If you want to look at someone's face and determine if they're angry with you or happy with you, if they're going to lend you money, if they're looking for money, you're going to look at their face and you're going to use your fovea to determine what's going on with their facial expressions, okay? And it projects back to the back part of the brain. And the point of this graphic is to show you is that we dedicate a lot of cortical space to our fovea, because just like our hands and our mouths, they're so important for our species. It's a very large amount of cortical area. Okay, now people get damage to their brains. Sometimes it's caused by accidents, sometimes it's caused by strokes. And depending on where the damage is, we can figure out in most people what they're going to be missing from their visual field, or vice versa. If there's something missing from their visual field, we're going to know what areas of their brain are damaged. So here, this particular person, when they look out at the world, is missing their whole right visual field. So then we know that the damage will be right here due to some sort of injury. If it's a smaller area, just up here in the quadrant, here, upper right-hand quadrant, then it'll be a little bit lower down here on the cortex. If it's just a small one here in this quadrant, it's a small injury here in the cortex. And that's how your visual maps are laid out. Okay, now I'm going to show a movie. I don't think we're going to need this because I understand it's tapped up. So let me just cue this movie up, Brian. Just give me a second. What you're going to see, I just want to make sure you understand what you're about to see, is a young boy who's growing up, and he lost his eyes to cancer when he was 3 years old. So he is completely blind. There's absolutely no visual input at all because he doesn't have any eyes. He's got glass eyes, right? Non-visual eyes. And what he does is he makes clicking sounds like a bat or a dolphin would. And he creates these sounds, and he did it on his own. No one taught him to do this. And he listens for the echoes off of objects and can navigate in his environment. It's absolutely astounding.
Says he can distinguish where the cars are as he cruises his neighborhood streets. Even though he can't see the basket he's aiming for, by listening for the distinctive echoes each makes, he can find the pole and backboard on a basketball goal and sink a basket.
It's easy to forget that Ben is blind. How else to justify my pleasure when I put a couple of goals past him? You thought you're so good. I am good. He is indeed. Ben beat me 5-2. Taking a walk with Ben, I was amazed at what he could see with his ears.
Well, there's a fire hydrant on the side and a car on this side. Like, is that not the trash can or that's hard to understand? That's a trash can? Yeah, trash can. Or recycling or whatever.
Playing video games with his brother Isaiah and the assault of noise. Ben can figure out everything that's happened just by listening. How can you even separate the sound?
Because they got different voices.
Nobody is going to tell him that there is an impossibility for him because there are none.
That doesn't give you any breaks because you're blind.
Nah. Why should he get a break? I can't get a break.
His mother, Aquilina George, insists he should have every opportunity, but no pity. But he's blind.
Doing that? I mean, you know, to society he's blind, but that doesn't make him happy. He just can't see.
Ben has much the same talent as the dolphins he visited at SeaWorld. The ability to use echolocation, returning sound waves, to sense his surroundings. His clicks even told him to step around a fallen trash bin. I don't know how you do that. But the secret to Ben's success goes beyond his clicks. Aquilina has always told Ben
once he said to me, he said, Mom, man, I wish I could see. And then I said, well, Ben, well, look what you can do. I said, if we had a blackout right now, everybody has to follow you. Why did you do that? He's going to applause you and he's to walk out. He's coming out of there without any applause. And his mother also. Hey, Ben, so bro. Shut up. All right, nice to see you. Nice to see you.
That's-
There you go, right there. Have a seat. Hello.
That's the end of it, Brian.
Welcome, Ben Underwood. You gonna fly down?
So that's been scientifically validated. There wasn't somebody half an hour before they shot the video going, hey, there's a trash can right there, or this has been scientifically validated. This is absolutely a true story. And he's not the only individual. In fact, this individual has helped other people who are blind to learn how to click and interpret the echoes. So it's fascinating. So here's my question for you before I show the next slide. When he's listening to the clicks, that's forming a map in his brain of the world that he can navigate through, where is that map in his brain? Where would it be? I hear someone saying vision. Let's look at the next slide then, Brian. So you know that at the back of the brain, it's the visual area. So when they say he's using clicks to see his environment, he actually is seeing. I'm sure it's a very different experience, perceptual experience than people with vision, but he's actually using the visual map to use the echoes. It's phenomenal. And that tells me that the way in which we describe that original brain that I showed you and where the visual area is and the language area and the auditory area, that's in neurologically intact people, that's in most of us. But these areas highly overlap, and these things are revealed when you lose a hand, or when you're deaf, or when you're blind. Okay, so a couple things perhaps we learned tonight. Your brain creates multiple maps of the world and have specific locations, and maps change with experiences like learning, drugs, and lesions. And maps profoundly overlap and can be reversed in cases of missing input like deafness and blindness. So back to our map of Canada and Lethbridge. So if we're going to use this metaphor, there really is a Lethbridge, but Lethbridge overlaps profoundly with other areas of Canada. So to extend our metaphor, maybe Lethbridge is also where people from Lethbridge now live. If I've said anything interesting tonight, if anything has piqued your curiosity and you would like to read more, this book was just published. You might recognize the first name, that's the guy that introduced me. You might recognize the middle name, that's the guy sitting beside the guy that introduced me, Ian Weshaw. And they brought me onto this book 2 editions ago. It just came out. So Amazon.ca, there you go. And that's my advertising spiel for the night. All right. I just want to acknowledge my funding and, of course, the students in my lab who've done the mapping projects. This is me standing in a canola field just outside of Yorkton, Saskatchewan. It's actually a play on words. It's me outstanding in my field. And I think we better leave it there. Thank you.